When a single sliver of cesium metal descends toward a pool of water, human intuition anticipates a fire. But we can see a different story if we look at the exact millisecond of physical contact, frozen in time before combustion begins. The standard high school chemistry curriculum relies on the heat and hydrogen model to explain what unfolds next. In this classical framework, the metal undergoes an exothermic reaction with the liquid. This reaction releases heat, which boils the water into steam while liberating hydrogen gas. And finally, that localized heat ignites the trapped hydrogen. Heat, steam, and burning hydrogen accurately describe the aftermath of the event. However, physical chemistry reveals that this model fails to account for the violent sub-millisecond burst that initiates the process. Relying strictly on a chemical combustion framework obscures the underlying mechanics. The initial trigger originates in subatomic physics. Standard exothermic reactions in water possess an inherent structural flaw. They naturally throttle themselves as they progress. As a normal metal reacts with water, the resulting heat produces a rapidly expanding layer of steam and hydrogen gas around the reacting material. As a flat metal surface reacts, the growing layer of gas bubbles forms a continuous barrier. This physical buffer separates the unreacted metal from the water, suppressing the reaction the same way a layer of foam smothers a fire. Cesium bypasses this physical limitation because the initial detonation originates from an electrostatic rupture rather than a chemical one. The event is a structural rupture driven by raw electrostatic repulsion, a process physicists call a Coulomb explosion. The violent flash observed upon contact marks the moment matter loses its ability to maintain structural integrity, tearing itself apart from the inside out. The mechanics of this structural collapse begin at the atomic level. Cesium is atomic number 55, positioned near the bottom of group 1 on the periodic table. This model illustrates a cesium atom's enormous scale, a 260 picometer radius with a dense core and vast empty space. At the absolute edge sits a lone 6s1 valence electron. Orbiting at such an extreme distance, the nucleus's electrostatic grip on it is exceptionally weak. Consequently, cesium possesses one of the lowest first ionization energies of any stable element. It takes almost zero energy to strip that distant valence electron away entirely. Cesium's extreme volatility is a result of this precise geometric vulnerability. The outermost electron sits on a hair trigger, ready to be donated instantly to any suitable acceptor. When a macroscopic cesium lattice comes into direct contact with liquid water, that hair trigger is pulled. In this cross-section, water serves as a highly electronegative acceptor, eager to pull loose electrons. Within picoseconds, millions of surface cesium atoms simultaneously donate valence electrons across the boundary. These electrons shoot into the water matrix and become solvated, leaving their host atoms behind. In less time than a single molecular collision, the rules of ordinary chemistry are bypassed, leaving behind a highly charged metallic structure. This mass electron donation creates a severe charge imbalance. Every surface atom that lost its electron is now a positively charged cesium ion. These particles switch to a positive state, yet remain packed at metallic density without their electron C. This invokes Coulomb's law. Like charges repel. Because they are densely packed, the electrostatic force is staggering, with every particle actively pushing against adjacent particles simultaneously. This internal repulsion transforms the cohesive solid into a compressed cloud of pure positive charge, expanding with staggering force. At the macroscopic level, we can watch that internal pressure overcome the droplet's physical bounds. The smooth surface of the liquid metal violently erupts into fine metal spikes and jets, projecting outward in all directions. This physical rupture is governed by the Rayleigh instability. As the positive charge density builds, it reaches a critical threshold, where the surface tension of the liquid metal can no longer contain the internal electrostatic repulsion. This structural, mechanical rupturing is the Coulomb explosion in action. Subatomic electrostatic repulsion violently reshaping macroscopic matter. This mechanical shredding explains why the insulating steam layer fails to stop the reaction. As this jagged metal spike tears open, we can see how electrostatic fracturing acts as a brutal, highly efficient self-mixing process. A runaway feedback loop takes hold. Each electrostatically driven spike rips the metal apart, violently exposing unreacted interior mass to the water. This fresh surface area instantly triggers a new wave of electron transfer, causing more repulsion and further fracturing. By mechanically blasting fresh fuel into the surrounding water, the metal physically pierces any protective vapor buffer that attempts to form. The physics of the Coulomb explosion mechanically forces the violent reactant contact that ordinary chemical fires lack, preventing the reaction from throttling itself. A definitive line exists between an ordinary chemical fire and a Coulomb explosion. Ordinary fire relies on reaction kinetics. Molecules must slowly diffuse, align, and cross an activation energy barrier to break and form covalent bonds over milliseconds or seconds. This split screen contrasts the two drivers. On the right, the Coulomb explosion is driven by net electric charge and electron tunneling, a mechanism occurring over picoseconds, roughly 1,000,000 times faster than the chemical combustion on the left. The classic markers of the event, the heat, the steam, and the fireball, are strictly the second act. The explosive flash we see here is the final chemical detonation that catches up to the physical fracturing process. Cesium's explosion is quantum electrostatics scaled up to a macroscopic level, an explosion of pure charge that dictates exactly how the subsequent chemistry must unfold.